This episode is brought to you by my friends at Patreon. If you'd like to join them and get early audios of upcoming episodes, please see the link in the description. It is somewhat peculiar for me, a staunch supporter of the gravity wells are for suckers philosophy, to contemplate the possibility of a colony on Titan. But of all the other worlds in our solar system, including Mars, though possibly excluding the Moon, which, for all its faults, still possesses the advantage of proximity, I declare Saturn's largest moon the most rational location for a permanent human settlement. This may be a hot take for my audience, particularly if, like me, they're fans of Isaac Arthur, who simply couldn't comprehend why anyone would want to make a home in Titan's sullen, leaden environs. But with all due respect to the unceasingly insolated Ohioan, speaking as a Londoner, there is an entire population of Earthlings, mostly clustered around this miserable mire, for whom sullen, leaden skies are the essence of home. Long, dark nights, overcast days, and the eternal prospect of showers are not the stuff of emo poetry, but the stuff of picnics. I can envision the Titan colony becoming the new British Empire, as we cluster around the freezing beaches and complain about the rain. With the Swedes, Dutch, and Norwegians along for the ride, we could establish a Nordic, service-based economy of stay-at-home data managers running on supercooled computers employing 80% energy conversion. Why is Titan the best locale in the solar system for Terran colonization? Well, for that, we must turn to an earlier techno-optimist, Martian prophet Bob Zubrin. In his 1999 book, Entering Space, Zubrin explores the options for colonizing the outer solar system and concludes that Titan is the most habitable world in the solar system after Earth. First, its great distance means that, unlike on Mars, the solar wind is weak, and that, together with Titan's thick atmosphere, lessens the need for radiation protection. Also, Titan's Earth-like atmospheric pressure means that a simple air suit, rather than a full pressure suit, would be required to traverse its surface. Titan's low gravity, roughly equivalent to the Moon's, and low ambient temperature, below 100 kelvins, would mean that a single human could carry enough liquid oxygen to last a week without having to cool it, while the methane in the atmosphere, combined with the oxygen in the tank, would provide enough energy for keeping warm. Keeping warm would be a problem on Titan, since its surface is made of superhardened ice, which would turn into an ocean at habitable temperatures. And this is my idea, not Bob's. We could solve this problem by employing the liquid methane lakes as a heat exchanger, and then pumping the warmed fluid into Titan's hotter inner layers. Those same inner layers could also provide water for any prospective colonists, since Titan's water-ice crust has been shown to independently float over an inner mantle of liquid water. On top of all that, Titan is rich in the elements essential for life: carbon, hydrogen, oxygen, and nitrogen. Assuming we could find sulfur and phosphorus, we would have all the raw materials to produce soil for growing food. Or, if our technology is advanced enough, construct food with 3D printers. And before you cry, "Everything will be automated by then. Why do we need to go?" The answer is simple. Someone has to fix the machines. One thing Zubrin does not mention is where prospective Titan natives could obtain their heavier elements, like iron, which would be difficult to access from Titan itself. For me, the most likely source would be Tethys, a small moon of Saturn that is apparently undifferentiated, meaning its heavier elements should be within relatively easy reach. Zubrin calls Saturn the Persian Gulf of the solar system, and not because of the hydrocarbons so readily available on Titan, which would be largely obsolete as a fuel source if and when we ever got there. No, the reason is Saturn itself. Our current hydrocarbon reserves, according to Zubrin, would, at current consumption levels, last us about 5,000 years. Saturn's hydrogen-helium atmosphere, again according to Zubrin, contains enough helium-3 to supply our current civilization with energy for 1 trillion years. Deuterium-helium-3 fusion has a higher energy-to-mass ratio than any substance found in nature, excluding antimatter, of course, but we are less likely to find an economical source of antimatter than we are a magic lamp. Jupiter could supply us with energy for twice that long, but its gigantic gravity well and ludicrous radiation levels make extraction uneconomical. The ice giants, which Zubrin suggests have a similar helium-3 richness to Saturn, and have the added advantage of lower gravity wells, are twice as far out. Fusion-powered rockets, fueled by plasma jettisoned from nuclear reactions, could reach speeds of 250 kilometers per second, fast enough to reach Saturn in about 20 months. Zubrin imagines a gigantic winged vehicle sifting through Saturn's clouds for the traces of helium-3, then rendezvousing with an orbital space station that would then send out the precious resource in giant space tankers. Zubrin sees Titan primarily as a source for supplies and materiel for the orbiting space station. Titan's small gravity well and thick atmosphere means that an 8-ton thermonuclear flight vehicle with an average speed of 160 kilometers per hour would require just 4 meters of wing surface to stay aloft. Essentially, none. Rocket launches would be correspondingly cheap, while the abundance of liquid methane, which is rocket fuel, on Titan's surface, would lower the cost of launches even further. So now that I've made the case for a colony on Titan, exactly what kind of calendar would it use? Only a select few objects in our solar system require calendars. Callisto, for instance, does not need a calendar. It has no weather and no appreciable seasonal differences in sunlight. The only people who would need to keep track of time on Callisto would be those tasked with orienting solar panels and transmitters toward the distant sun, or those tracking launch windows for the various planets. Anyone else, snug in their underground habitats, would happily use the calendar of the motherland. Ditto Pluto, which lies so far from the sun that any required seasonal adjustments would occur on timescales beyond human lives. The moon also doesn't need a calendar because, since Earth's dominant calendar is lunisolar, it already has one. Venus, on the other hand, needs a calendar. The only way to survive on Venus is above the clouds, where constant monitoring of the sun would be required to ensure that the monster in the sky does not fry circuits or dirigibles. Mars, as I said in my previous video, needs a calendar. Its seasonal differences are so extreme that unmanned rovers and landers have been destroyed by them. And Titan, of course, needs a calendar. Not only would its week-long nights hinder outward exploration, but its Earth-like seasons, spread over Titan's 29.5-year year, dictate when the rains will fall and at which latitudes. When Cassini observed Titan for half a Saturnian year, 13 Earth years, it noted that the desert-like mid-latitudes only saw methane rain during the springtime, and models suggest that the hydraulically produced landscapes observed by the Hauchens-Lander were likely produced by once-in-a-millennium flooding. Waiting for the rains will likely be as mythic a process for Titans as it is for Earthlings. Just like on Earth and Mars, Titans will likely cluster in the high northern latitudes, where the permanent bodies of liquid reside, and the rains apparently occur in summer. Also, once-in-a-Saturnian year events like the Dragon Storm or the Great White Spot would be presumable times of celebration for Titan. So how would they mark these times? I have to say I did not invent this calendar myself. I owe this particular set of calculations to a user known as Grapes on a science forum I frequent, which often serves as my last port of call when research fails. He, very graciously, provided the necessary work in response to a question I asked in 2015. Here it goes. Titan, like all large moons in the solar system, is in captured rotation. One of its days is equal to one of its orbits around Saturn. In practice, this means that one side always faces Saturn, and another always faces away. If you could see Saturn from Titan's surface, which, despite the imaginative leaps of artists, you decidedly cannot, it would only be visible from the facing side. This does not mean, however, that either side is permanently in day or night. Each experience exactly 1 day's worth of daylight. Titan's rotation period, or sidereal day, is 15.945 Earth days long, while Saturn's year is 10,755.7 Earth days. Taken together, these two facts mean that Titan's synodic day, that is, its day from sunrise to sunset as viewed from the surface, is 15.968665 Earth days. A Saturnian calendar year would thus comprise 674 Titanian days, with 0.229225463 Titan days left over. This is surprisingly similar to our own calendar's annual remainder, and can be fixed in a similar fashion, with a leap year every 4 Saturnian years and a dropped leap year every 48 Saturnian years. For the excessively accuracy-minded, one extra leap year added every 16,992 Saturnian years, a time span longer than our species has existed on this planet, would make the calendar accurate to within 20 minutes. Over the course, may I remind you, of a 16-day day and a 29-year year. Of course, a calendar needs further subdivisions, and again, nature has been very kind to the natives of Titan. For Titan's day is almost exactly 16 Earth days long. So close, in fact, that keeping the two time spans in sync would require the addition of just one Earth day every 510 Titan days, or about 5 times every 4 Saturnian years. For those confused, this is a 17-day-long Titan day, rather than 16 days. The leap days I was referring to in the previous section were Titan days, all 16 days of them. This grants Titans an 8-day week, in much the same way that the Romans had a 12-hour day and a 12-hour night. Again, for the confused, the length of the Roman hour changed with the year. It is easy to imagine the lives of Titans falling into an 8-day rhythm. During the long Titan day, spirits would be moved to outward exploration and station maintenance, while the long night would be a time to focus on internal matters. As the 8-day week supplants our 7 days, perhaps the number 8 will take on the same significance among Titans that 7 does to us. The real question is, how would Titans see their year? With an 8-day week, would they bother with a 365-day year? Possibly. After all, we have never cared that 52 7-day weeks only adds up to 364 days, and keeping the calendar of the homeland would enable communication with relatives and easy celebration of holidays like Christmas. But over time, as their culture diverged, it's easy to imagine Titans going native and adopting a calendar more in tune with the cycles of their homeland. Perhaps a calendar of 46 8-day weeks, totaling 368 Earth days. Or perhaps Titans could completely surrender to the frigid rhythms of their home and count time in its own gargantuan years. Puny Earth years be damned. Calendars have always reflected the mystic impulses of their creators. Unlike the future inhabitants of the Moon or Mars, whose calendars huddle close to the cycles of Mother Earth, a calendar on Titan will mark grander, epochal cycles that encompass the lifespan of humanity itself. What mystic impulses will it impart to those who follow it?